Somewhere in a farm field in the early 1900s, a steam traction engine sat pulling a threshing machine, its boiler roaring at full pressure. And if the man running it made one specific mistake, that engine could kill everyone standing near it. This isn't an exaggeration. Steam boiler explosions were a real documented hazard on farms a century ago. And the difference between a safe afternoon and a catastrophe often came down to one small, cheap piece of metal almost nobody talks about today. In the next few minutes, you'll find out exactly what could turn a working steam engine into a bomb. You'll see the strange, almost accidental-looking device that was often the very last thing standing between a farm crew and disaster. And you'll understand why the safety habit built around it still shapes how engineers think about risk today. This is documented agricultural engineering history, not folklore. It starts with a machine that looks simple from the outside and is anything but simple on the inside. By the late 1800s, steam traction engines were doing the heaviest work on American farms, pulling plows, running threshing machines, powering entire harvest crews. The idea was simple enough: burn coal or wood, heat water in a sealed tank, and use the pressure of the resulting steam to drive the engine. Here's the strange part almost nobody expects. The danger wasn't really the fire. It was the water. Inside the boiler, metal tubes or a firebox wall sat directly in the path of the flame, with water surrounding them to carry the heat away safely. As long as that metal stayed covered in water, it stayed at a manageable temperature. But if the water level dropped even a little too low, that metal was suddenly exposed straight to open flame with nothing to cool it. The metal would overheat and weaken in minutes, sometimes far less. And when overheated metal finally gave way, it didn't leak. The water still inside flashed instantly into steam, all at once. That sudden, violent expansion is what actually tore a boiler apart. Not a slow leak, a catastrophic, instantaneous failure. In 1866, one insurance company, the Hartford Steam Boiler Inspection and Insurance Company, began keeping records specifically because of how often this kept happening. Low water. Again and again. Low water. Sit with that for a second. The machine that powered the harvest could become a weapon aimed at the very crew running it, from a mistake as simple as not checking a gauge. So farms running steam power needed something better than hoping the operator never got distracted. And keeping a fire-breathing, water-filled steel tank under pressure, reliable enough for daily farm work, wasn't going to happen through luck alone. Here's the part most people never hear about: how that problem actually got solved. Every steam traction engine came with a daily ritual built around exactly one number: the water level. Before the fire was ever lit, the operator checked a water gauge glass, a thin tube on the side of the boiler that showed exactly how full it was. Once running, he'd glance at that gauge constantly, refilling water as it boiled away, and watching the pressure gauge just as closely. Every so often, he'd blow down a valve to clear sediment that could clog the works and throw the water reading off. And there was one rule every operator was taught never to break: never tie down or block the safety valve, no matter how tempting more pressure sounded. What no one expected was that the real last line of defense wasn't a gauge at all. It was a plug, screwed directly into the hottest part of the boiler, the crown sheet. Right above the fire was a small plug made of a soft lead alloy. The detail almost no one mentions is that this plug was designed to fail on purpose. It was engineered to melt at a specific, predictable temperature, hot enough that it would never melt under normal operation, but well below the point where the surrounding steel would actually give way. If the water level dropped low enough to expose that spot to direct flame, the metal around it would heat past its melting point long before the boiler itself was in danger. The plug would melt first, and steam would come shrieking through that small hole into the firebox with a loud, unmistakable hiss. Here's where the story usually stops in most retellings, but the clever part is what that hiss actually did. The rush of steam into the firebox helped smother and cool the fire immediately, taking heat away from the exact metal that was in danger. At the same time, that hiss was loud enough that every single person nearby knew instantly something was wrong. A 5-cent plug had just bought the crew critical seconds to react, get clear, and shut the engine down before the boiler itself had any chance to fail. Nobody had to be a genius to notice the warning. The whole point was that you couldn't miss it. Manufacturers of the era stamped these plugs with the exact melting temperature they were rated for, so a crew could check that the right part was installed before ever firing up the boiler. Get the wrong plug in there, one rated too high, and the whole safety idea quietly stopped working without anyone realizing it. But that's not even the cleverest part of the whole design. Notice what the engineers actually did here. They didn't try to make the boiler indestructible. They deliberately built in a weak point, on purpose, in exactly the spot they wanted trouble to show up first. The stranger fact is that this is the same basic principle behind an electrical fuse in your own house today. A fuse is designed to be the weakest link in the circuit, so that if something goes wrong, it burns out first and protects everything more expensive and more dangerous behind it. The fusible plug in a steam boiler did the exact same job a full century earlier, using nothing but the melting point of a metal alloy. It wasn't a backup system bolted on as an afterthought. It was the entire safety philosophy, engineered directly into the boiler itself. Records from steam engine safety historians describe this as one of the most elegant fail-safes of the entire steam era. No electronics, no moving parts, nothing to break down on its own. Just a specific alloy, chosen because of the exact temperature at which it stopped being solid. Think about how confident you'd have to be in that one small detail, knowing a crew's safety depended on it every single day. And it worked precisely because it was simple. There was nothing in that plug that could jam, corrode into uselessness, or be second-guessed by a distracted operator. The safety valve handled too much pressure. The fusible plug handled too little water. Between the two, most of the ways a boiler could actually fail were covered by devices that needed no judgment call at all. Here's the detail that still surprises people who work with historic machinery today. A well-maintained plug from this era could sit in a boiler for years, doing absolutely nothing, and still be trusted completely the one time it actually mattered. That's a strange kind of reliability, a safety device whose entire job is to do nothing, right up until the exact moment it matters most. Here's a question worth sitting with. How many other dangerous machines from that era survived not because people got more careful, but because someone designed the danger out of the equation entirely? Here's the part worth knowing if you've ever seen a steam traction engine at a county fair or a working museum. That little plug isn't decorative, and it isn't a modern add-on for insurance purposes. Preserved and restored steam engines still running today carry a fusible plug for exactly the same reason farms did over a century ago. Boiler inspectors checking these engines for public operation still test that plug specifically because the principle never stopped being sound. Stop and think about that for a second. A piece of engineering from before electricity was common on farms is still the exact same solution used today, unchanged. The old engineers weren't just being cautious. They built one of the simplest, most reliable safety devices of the entire industrial age, using nothing more than a metal that knew exactly when to give up. Here's the last piece of this that most retellings skip entirely. None of this required the operator to be a trained engineer. It required him to trust a 5-cent part he probably never had to think about twice. That's worth pausing on for a moment. The safest machines aren't always the ones that demand the most vigilance. Sometimes they're the ones designed so the vigilance barely matters. So the next time you see one of these machines running, steam hissing, pressure gauge steady, you'll know exactly what's quietly standing guard inside it. That's the real story, documented and still trusted in working steam engines today. If you want more of these, the real engineering behind the machines we walk past without asking how they actually worked, subscribe to The Quiet Farmer. And tell us in the comments, have you ever seen a steam engine running in person?